All right, so today's lesson we're talking about relations and functions. And I'm just going to go over this with you. If you want to put it in your notes, that's great. If not, don't worry about it. Really, I just want to go over this part with you, and then I'll give you examples, and that stuff you're definitely going to want to have in your notes. So a relation is just a set of ordered pairs, X, Y's, so to speak. And technically, it's like something is happening to one to get you to the other, right? If we input something for X, it's going to give us a specific Y. And they can be shown in a table, right? There's all sorts of ways to show them. We show them in a table by mapping, and I'll show you what each of these mean. You guys have seen graphs before, but I'll show you how they set relations, or expressed as an equation. Now on a graph, it's easy because it's a set of ordered pairs. It's X, Y. So it's shown by points on a graph. The set of X values in a relation. So all of your X values make up what's called the domain. You hear a lot in algebra about domain and range, but really all they are is the domain is all of your possible input values or your X's, and the range is what all of your possible Y values can be, right? Or your outputs. A relationship with distinct points is called discrete. So if you see a graph and it's just got points, it would be considered a discrete relation. But a relationship where it's connected and smooth and it flows together and there's points between the points and they're always going to work out, that would be called continuous. But what we're really moving into is functions. This unit is an introduction to functions, specifically linear functions in this one. And a function is just any relation in which each element of the domain, each X value, would be paired with exactly one element of the range or the Y values. Every X has to pair with something, every Y possibility doesn't. And every X can only pair with one Y, right? And I'll show you what I mean by that in mapping in a little bit. Function notation, I'll go over this more specifically as we get to it. It's just basically saying your output becomes f of x. X is the input and f of x is the output. And I'll show you how that works when we start looking at those problems. Evaluating functions, when you're evaluating anything in mathematics, if it tells you to evaluate something, it's going to give you a value, and all that means is you plug it in for whatever the variable is and you solve it. In this case, if we were going to plug in -3 into this, we would plug it in for x and we would solve it. And the rest of the time, I'm just going to give you examples of all of these things that we just talked about. So when we're talking about relations, we can look at sets of ordered pairs, right? And what I mean by that is, say I have we're going to look at the difference between relations and functions, right? And that's kind of what we're talking about now. Is it a function is what everything is. Everything I show you will be a relation. Will it be a function is what this lesson is kind of about, right? So if I have a set of ordered pairs, right? Let's show you let's see if I can make that. I can never make those really well. Say -1, 9, 0, -5, 4, 3, 6, -2. And I've got all of these ordered pairs. That's all this is, right? This is a point. These are each an x, y value. It's just a set, because they're contained in this thing, of ordered pairs. And if we want to know whether it's a function, here are the things that we need to look at. The first thing we need to look at are x values. Do any of them repeat? In this case, none of them repeat, right? So I can say right now that because my x values are all matched up with a y value, each one has a y value, none of my x values repeat. So I could say that this is a function, right? The domain of this function, if I was asked to give it domain, I don't know where I was going with that spelling. The domain is all of our x values. So our domain would be -1, 0, 4, and 6. That would be the domain of this function. The range of this function would just be our y values. So it would be, we want to do them in order least to highest. So they would be -5, -2, that's a negative, 3, and 9. Right. That's all we're talking about with domain and range is what are our possible x values? Well, in this set, every x value is a possible x value. So that's our domain. What are our possible outputs? Well, anything that's a y within this function. And so that is one way to determine a function. So if I had a different function, if I had a different example, let's look at this set right here. 5, 2, -3, 4, 5, -6, comma, 8, 0. And I ask, is it a function? The first thing I'm going to look at is my x values. Do any of my x values repeat? And in this case, they do. So I'm going to say no, it's not a function. And if I asked you, okay, well, it's not a function, but what is the domain? And what is the domain of this relation? It is a relation, right? And what is the range? In this case, we would just go, okay, well, the domain is 5, -3. We don't have to list 5 again. 8. Technically, I should have them in order least to highest, but doesn't matter so much. My range is my y's, right? So it's going to be, I did them in order, -6, 0. I lost my order. -3 and 4 and 2. Did I miss something up here? -3, 8. Do I have too many? I have too many. This way. 2, 4, -6, and 0. I don't know where I was getting my numbers from. 2, 4, -6, and 0. That is my range, right? It's all my y's. Right? It's every one of these right here. And so when you're looking at a set of ordered pairs, all you want to do my eights, do my x values overlapped. If any of them are the same, then I'm not going to have a function. Well, technically, like if they both mapped to the same number. So if I have 5, 2 here, and then again I have 5, 2, it's still a function because 5 and 2 are still the same association. But you're not likely going to see something with two of the same points on top of each other. So we talked about sets of ordered pairs. We also we talked about a table, right? Another way to tell with a relation, if a relation is a function is if we have a table. Well, a table is just another way of showing a set of ordered pairs. And you guys have seen these tables before, but if we have a set, is it a function? If I have a set on a table and I have something like boom, boom, X and Y, and I have, say, 7, -8, 2, 3, 0, -1, and -4, 3. And I'm asking you, hey, is it a function? Just like the set of ordered pairs, I can come down here and I can go, do I have any overlapping x's? Do any of my x values repeat? The minute that I say no to this, I can say yes, it's a function, right? So what if I ask the question again and I have a different table? Like, do I have a table that... And it's... So this one's yes, right? If I have 7, -8, 4, 2, 3, 7, 4, -6. If I'm asking whether or not this one's a function, it would be no, because our 4's repeat, not a function. All right, so it looks the same way. We're just presenting the ordered pairs differently. So another way to determine between a function and a relation, like they're all relations, right, is we said mapping. If you go back, you can see one of the items we had was mapping. So let's look at what that looks like. So if I have a table and in it I've got like -4, -2, and 5. And then over here I've got my y's. And let's say we have 0, 3, 7, and 9, right? We'll put a big oval around it. And I go, okay, well, the 4 maps to the 0, right? The -4. The -2 is going to go to the 3. And the 5, well, it's going to go to the 9, but it's also going to the 7. And here's the question again. Is it a function? And the answer in this one would be no. And the reason is, remember we said all of our x values can only pair with one y value, right? So simply because this 5 goes to 2 separate numbers, it is not a function. Let's look at another example. And if I wanted to, if I asked you what the domain was of this, well, your domain would just be -4, -2, and 5, right? Your range would be whatever is your in your y circle. And in this case, it would be 0, 3, 7, and 9. Because relations, even though it's not a function, it's still a relation, and it does have a domain and a range. Let's look at another example. Ooh, that was an awful example of what an E should look like. So say I have my X's. Let's move up a little bit so you guys can see. And they are 2, 8, 13, and 17. Right? Put them in an oval thingy. It's hard to draw with this. I'm not good at it yet. And I've got my Y's, and they are, let's go -4, 0, and 7. And we've got 2 goes to 7, 8 goes to 0, 13, let's take that all the way up here to -4, and 17, let's match that to 7. Now, if I ask you, is this a function? All of our X values only map to one thing. None of them repeat, right? Now, it doesn't matter that 7 has 2 things pointing to it, because our range can have multiple matches, but our domain cannot. So our X values, each X value has to map to something, right? But it can't map to more than one thing. But our range can have more than one thing mapped to it. So even though this 7 has 2 things pointing at it, it's okay, because 2 only goes to 1, 8 only goes to one thing, 13 only goes to one thing, 17 only goes to one thing. So we can say, yes, this is a function. It is a function with a domain of 2, 8, 13, and 17, right? And a range of -4, 0, and 7. And it's a really important part of functions. I'm going to give you one more example of how to tell, and that would be on a graph. It's going to be a really rough example, but we also have something called the vertical line test. And when we're determining a function on a graph, we can use what's called the vertical line test. And the vertical line test is pretty easy to work with. It's saying if I have a graph of something, right? So say I have a graph of something like that. Doesn't matter what the shape of that graph is. If it is a function, if I drop a vertical line into it anywhere within the graph, it will only cross in one spot. So anywhere I drop a vertical line, it's only going to have one point where it intersects. So if I look at that, I can go, oh, this is a function. Just by looking at the graph of this, I can tell it's a function. So say I have something like the graph of a circle. If I drop a vertical line in through this circle, Sorry, that should be straight up and down, but you get the idea. But it's going to cross at 2 points, right? And we can say that is not a function, right? So if anywhere within the graph of the equation, because that's all these are, is graphs of equations, we can determine whether or not it's a function by whether or not we can drop a vertical line through it. And honestly, my vertical line should be straighter than that, but you guys, I think, get the picture. So that is how you can kind of tell whether something is a function or not. What else we got for you? Oh, we want to talk a little bit about function notation. When we're talking about function notation, I know I went over it a little bit up above in your definitions, but function notation, you see a lot of this. You see f of x, or you might see g of x, or h of x. All this is a notation. It's the name of the function. We aren't doing anything with this x. I know usually when you see something in parentheses and it looks to you, it might look to you like f times x, but it's not. How you would really interpret this, you would say it as f of x. And what it means is we have a function named f, and then with an input value, with an input of x. It means x is the variable, right, that we're inputting for. It is our independent variable, right? This one says we have a function named g of x, right? We call it g of x, which means that we have this g, that's the name of the function, and it has an input of x, right? So if I saw something that said G3, it would mean everywhere in the equation that followed, right? Say it's x plus 3, where I have an x, I'm going to put in a 3. It's my input value, right? And that'll be really important when you're actually evaluating the functions. So if I have, say, for example, if I have 2x, y equals 2x plus 7, right? I think that's the one I used up above, right? When I write it in function notation, I can just replace the y with f of x. And now I have 2x plus 7. And that is the same thing written in function notation. So you can interchange those. If you see f of x, you can just write it as y. And it helps a lot to think of it that way when you're doing like a table or something and you're trying to figure it out. Now, when you're evaluating a function, it's an input, right? So if I say evaluate the function, evaluate at f of -3. I was trying to remember what I used before up above. It just means that here I have this equation, right? This f of x equals 2x plus 7. It means what I'm going to do is I'm going to have y equals 2 times -3 plus 7. And we're going to figure out that solution. We're going to go ahead and solve it. 2 times -3 is -6 plus 7 equals 1, right? So f of x, or f of -3, equals 1, right? All it is we input it and we solve. So let's look at a couple of other examples. Let's start right here with, I have a function, my function f of x is going to be equal to minus 5x minus 14. And we'll have ourselves a g of x, right? That's going to equal minus x squared plus 9x minus 1, right? When I look at this, I'm going to do a couple of examples, so I'm going to number them. What if I want f of negative 9? Well, to do that, I'm going to look at, well, I'm going to use my f equation, and I'm going to go, okay, negative 5 times x, well, x is just negative 9 minus 14. And then I'm going to solve it, right? It's going to equal, well, that's 45 minus 14, which is just 31. And this is going to be my solution for f of negative 9. What if I have, let's go with something crazy here. Let's go number 2. 2 times g of 12, right? That's sort of a crazy looking problem when we think about it. But it's not so bad, really, because what is it saying? It's saying, well, I've got 2. I'm going to put the bracket back there, right? And I'm going to go g of 12, which means I'm going to take this equation, and anywhere I have an x, I'm going to put 12 in, right? So I'm saying I've got 2 of g. So let's just put in 2 of g. 2 of g would be 2 of x squared plus 9x minus 1. But everywhere there's an x, I am going to put in 12. So really what it's saying is 2 times negative 12 squared plus 9 times 12 minus 1. I hate it when it corrects sometimes, because sometimes it corrects wrong. And when we look at that, now we can solve this. This is just mathematics, right? If you have a calculator, you can do it. So here I have minus 12 squared. Well, that's 144. Plus 9 times 12. What is 9 times 12? Is that like, I want to say 72, but I don't think I'm right. For some reason, I can't remember my 12 times tables right now. 9 times 12 is, see, 108. I was way off. Plus 108 minus 1. And so if I look at this, I've got 104 minus 1, 144 minus 1, 144 minus 108. So I've got negative 36 right here. Minus 1 is negative 37. So now I'm left with 2 times negative 37, which equals, I don't know, 2 times 37, negative 74. So I needed a calculator for that. I could have done the math as side work, but I didn't bother, right? But we can do this. It's just a plug and chug, right? You just plug numbers in. So if I had, for a last example, to get us another simpler one, say I have g of negative 7, right? Number 3, we've got g of negative 7. We're going to go back up and we're going to look at our g. Well, our g was negative x squared plus 9x minus 1. And it just means that wherever I have an x in that, I'm going to put in negative 7. So I have negative 7 squared plus 9 times negative 7 minus 1, and we can just go ahead and solve. And we're going to wind up with negative 49 minus 63 minus 1, and we're going to add all those together and give them a negative. So it would be minus 50 minus 63, which is minus 113. So sometimes I can do the math in my head and sometimes I can't. So you're going to have some problems related to that in whatever that delta math. So do your delta math assignment. I think it'll be fine for you. I think you guys will do great with it. And let me know if you have any questions, and I'll be happy to help. So.